Right, so this fourth handout that you've got then on linear motion, or the equations of motion, is this one here. So what I want to do is just sort of introduce these equations of motion in terms of both linear motion and angular motion, rotation, because there's two sets of equations that are equivalent. So you've got the notes in front of you. I don't know how much extra you want to take in terms of the notes I'm going to give you here. That's up to you. I'll put these on the site as normal. So linear motion, first of all, we sort of consider it being motion in a straight line. So moving along like this. So some object is moving along with a velocity v, and we plot a graph of velocity against time, and this is what we get. So straight away, what can we say about the motion of this object? And that's what we can't say, James. If the speed was constant, that's the speed. If the speed was constant, I'd be like this, wouldn't it? Yeah. Yes, it's accelerating. Can we say anything else about that acceleration? Or right, it's a uniform acceleration. So this is representing uniform acceleration. Uniform because we've got a straight line. It's not speeding, increasing acceleration and then slowing down the acceleration. It's a constant acceleration. Uniform acceleration, constant acceleration. What is it about this line that represents the acceleration? Could we calculate that acceleration? The gradient of the line, right. The gradient of the line gives that acceleration. Okay. We have some quantities that we define to do with things moving like this. So we call the S the displacement. That's the vector equivalent of distance. So displacement S, measured in meters generally. And then we have u and v. So u represents the initial velocity. So we might say that this thing is starting off with an initial velocity here of u, and then it's increasing its speed. So we might be interested in what is its speed at that time. So there, say, so v would represent the final velocity after a certain amount of time. A would be the acceleration that we could calculate, and t is the time. And then we have some formulae that we can write down that's associated with these quantities. And the first formula that we can write down is that velocity, final velocity minus the initial velocity divided by the time, which is actually what you do to find the gradient of that line, v minus u over t, gives you the acceleration, equals acceleration. So that's a formula we can write down that relates acceleration, v, u, and t. And we can rearrange that formula and arrive at one of the common equations of motion that we're going to write down in a minute. Another thing we can find out is if we look at this motion here, we know that the velocity is not the same. It's changing all the way up this line. The velocity is changing. So say I was interested in what the velocity was between here and here. Well, the velocity is increasing. We might find out what the average velocity is. So we would say if between that point and that point, assuming it's a constant acceleration, which this graph is telling us, then the average velocity would be the midpoint, wouldn't it? And so we could find the average velocity by adding the initial velocity to the final velocity and dividing by 2. So we can come up with another equation, v plus u over 2 equals what's called the average velocity. So that's the average velocity. So that's two things we can sort of write down about this motion. And then from that we can come up with some others. For example, that the displacement, let's write it in terms of the velocity actually, the average velocity so average velocity equals displacement over time. Velocity is displacement over time, a common formula you've all used. The big assumption for this formula is that the velocity is constant, isn't it? So if you're using the formula velocity is distance over time, we're assuming constant velocity. In this case, it would have to be the average velocity we're using. The average velocity over this will give us displacement over time. If I rearrange that formula for displacement, that equals the average velocity times the time. And if we go back to this curve, so I want to find out what the, if I'm considering a couple of points on this curve, here and here, say, so T1 and T2, these 2 points, the area underneath this curve between those 2 points, which is the average velocity, if you think about it, if I were to take the average velocity, which is this point, say, the average velocity times by the time gives us the area underneath this curve, which is the distance travelled from that formula we've just written down. So actually the area under the curve between 2 points gives us the displacement. Those of you who've done some calculus before will know that actually calculus is going to come in handy with curves like this, because differential calculus helps us to find the gradient. So that would help us find out what the acceleration is if this was not a uniform acceleration. And the area under the curve would be given by the integral. So calculus is going to come in handy when we look at problems like this later on. So there we have these formulae. And we can now play around with these formulae and end up with 3 more equations, commonly known as the equations of motion, which are V equals U plus AT, that you know, I think, S equals UT plus a half AT squared, and V squared equals U squared plus 2AS. And I'll leave that as a little exercise for you, algebraic exercise, if you're interested. All those 3 formulae can be arrived at by considering just the ones we've looked at. By rearranging those formulae and making certain substitutions, we can come up with these equations of motion. And they've been derived because each of them has certain property that's useful. If we look at the first one, there's no displacement in that formula. So if I've got a problem to address where I'm either not interested in or I don't know what the displacement is in this particular situation I'm considering, then I might be looking at this first formula here, number 1. So in that one, there's no S. No displacement, so that can be useful sometimes. And the other 2 have been designed so that something's missing in those as well. If you look at the second one, there's no final velocity. So if I'm not interested in the final velocity, or I don't know what it is, I would perhaps use the second one. And what's missing, the obvious thing that's missing in the third one? T, yeah. So if I don't know the time, or I'm not interested in it, then that's the one I'd be looking for. So they've been arranged like that for that reason, really. So we've got those 3 equations of motion, plus the other 3 there, that we can use to solve problems involving motion of something, linear motion, like this, of some object moving with a velocity for a period of time If that velocity is changing, we can find out all sorts of things about this motion. So now we need to have a look at some examples of problems.